This is lecture video 34, and in this section we present the fundamental theorem of calculus, which is the central theorem of integral calculus. It connects integration and differentiation, enabling us to compute the integrals using an antiderivative of an integral function rather than by taking the limits of Riemann sums. And we start this section by presenting an integral version of the mean value theorem, which is stated here. We covered this theorem before, where we called this part as the average value of f. And now the mean value theorem for integrals, this stated version here, adds one more detail to this average value, like left-hand side can be represented as an image of the point C under our function f. Okay, so recall that before we stated this theorem as average value of f is given by this expression divided by the length of the interval. As you can see, b minus a is the length of the interval. So we can understand this equality geometrically by thinking like there is an area, shaded area here under the curve, right? If you think it like you transform or you move this area to here, then the result of the integral, this part will be what? It is kind of the area of this triangle, right? So here we can see that the definite integral, the value of it is given by, okay, now we can call this point as the average value of f, is given by the height times the base of this rectangle, right? Times the base of the rectangle, so that it will give somehow the area under the curve, where we can find it by using this definite integral. Okay, so here maybe I need to give an example. Okay, so let's consider this function f of x equals minus x squared over 2, and let's consider it over this closed interval from 0 to 3. And let's compute f average first, and then we will try to find the point C in this integral such that the image of C is exactly what we found as the f average, okay? So first of all, let's compute average value of f. It is from this formula given by from 0 to 3, these are the endpoints of the given closed interval, this definite integral divided by the length of our interval. Okay, it is then not, it is, we know how to compute these definite integrals by using antiderivatives now. So what is the antiderivative of this function? Minus 1 over 2 stays as a constant coefficient in front, and the antiderivative of x squared is x cubed over 3, and then we can safely insert upper lower bounds like this, and at the denominator we have just 3. So what we have, it is minus 1 over 2 times 3 cubed over 3 minus minus plus, then I insert 0, right? 0 cubed over 3 divided by 3. So the result of this computation is minus 3 over 2. Now, I want to search for an real value for a point f of c such that it gets this value. So our function is x squared over 2. So f of c is minus c squared over 2. I want to find such a point c whose image is minus 3 over 2. So this is what mean value theorem for integrals say. The result of the average value is taken by some point C. Here it is, C in your domain, and its image will be the same as your average value. So can we solve the point C from this equality? Of course we can. Here we see that C squared is 3, so C is either plus square root 3 or c is minus square root 3, but look at our interval. Our interval is from 0 to 3, that's why you can just eliminate this one. Okay, that's the point we search for. So let me show you what we have found here through the graph. So minus x squared over 2 is a curve like this. Okay, and we computed its average value over which interval? Over the interval from 0 to 3. Okay, and so that average value turns out to be minus 3 over 2. And this minus 3 over 2 is attained by some point C in our interval. So it is attained here by some point C, okay, in our interval. So this point C is computed here as plus square root 3, okay? So that's it. Let's move on. Next theorem is the fundamental theorem of calculus, part 1. Okay. And as I said in the introduction, fundamental theorem of calculus relates the integral and the differentiation. It's a very strong tool in calculus course. So let me write this down here. So calculus course consists of two main topics like differentiation and integration. And the very strong tool that relates these two topics is the fundamental theorem of calculus, which we will cover soon. And I will be using this shortcut for it, fundamental theorem of calculus. And it has two parts, fundamental theorem of calculus part 1 and fundamental theorem of calculus part 2. In part 1, it will say something like this, okay? So we will have an integral from a to x of some function f t dt, and after taking the integral, we want to take the derivative. You see, we apply integral and derivative after one another, and as we know that they are inverse operations, we expect to find the original function itself, right? I will explain this. And fundamental theorem of calculus part 2 will give us, here we just change the ordering, okay? So we will just first apply derivative to our function and then integral to it. Let's say from a to b, then the result will be something like this, okay? And I will explain this part 1 and part 2 in more details. So I just want to put this diagram here before we start. And let's also say that integral and differentiation, they are inverse operations. Okay, so let's look more detail into fundamental theorem of calculus part 1. Here, the ordering is important, as I said. First, you take the integral, and then you take the derivative. Somehow, you neutralize what you did in the first step by taking the integral. That's why we expect to left with the original function itself again, right? But with only one difference, because after you take the derivative here, after you take the integral here, the result of this definite integral depends on x, obviously, right? Depends on x. And then it makes sense to take the x derivative of this expression, which is the result of the integral depending on x. So you can safely take the x derivative of it. So the result, overall result, will depend on x, obviously. And since derivative and the integral are inverse operations, we will end up with original function again. And by the way, here a is an arbitrary constant, okay? So this is what we call as the fundamental theorem of calculus part 1. Here is the first example about that, okay? Maybe before moving to the example, I can try to show you where, I explained it, but We can also prove it by writing algebraic computations. Okay, so this is what we want to do. And then we want to take the derivative with respect to x. And we know that this big letter f is the antiderivative of our function, okay? That's why the result of this integral, it is already given in the statement, you see? The result of this definite integral is denoted by big letter of f. So what we have, something like this. And since this is a definite integral, I need to insert these boundaries. So you see, the integral is from a to x. That's why you are inserting these boundaries here. Okay. And then what we have inside, this is, I think I should have used the t notation instead of x, because it is written here like that. So, and it makes more sense, in fact. So now you can insert x for t and then a for t. If you insert x, you will have f of x, and then you subtract f of a here. So we can take the derivative now. Derivative of this constant is just gone, right? After taking the derivative. And what is the derivative of this thing? Since we know that, okay, the result here is this, and since f is the antiderivative of big letter f is the antiderivative of the small letter f function, its derivative will be our function, okay? Because we have such a relation between f and small f and big f, like this is derivative is our original function, antiderivative, in other words, the integral of it is the big letter f. So you can prove this theorem easily, quickly like this. And let's apply it here. Y function is given like this, and we want to find the x derivative of the given y function. So what we want to do is the following. And then take the derivative. This exactly fits to the situation where we can apply fundamental theorem of calculus part 1, because you first apply integral and then derivative, which are the inverse operations. So by fundamental theorem of calculus part 1, all you need to do is to insert this variable x for the variable t here. So this is our f of t, right? And the result is supposed to be f of x. So you are just changing the variable t to the variable x. So the result is quickly like that, which is the function f of x, okay? And let's look at this one. Here, it still fits to the structure. We want to take the derivative of the given y function in terms of x. Okay, d over dx of this integral. You should be careful about the structure of the integral here. The constant should be always at the bottom, at the lower boundary, okay? But what we have in this example is the constant number is in the upper boundary, but we know how to exchange these boundaries, right? We can just exchange the places of the upper lower bounds. So you can take 0 here, right? Square root x here, t squared dt. And you need to put an extra minus here, right? Because changing the boundaries affect the result like this. Okay, and then you want to take the derivative, of course. Also, there is one more generalization here. Instead of x, you see here we have x, but instead of x, we have square root of x, which is a function of x. So this is, in fact, kind of the generalization of fundamental theorem of calculus part 1. So let me first explain it here. Say more generally. What if you have not x, but some function depending on x here for the upper bound of the integral, and you still want to apply the fundamental theorem of calculus? you can still apply it. Fundamental theorem of calculus part 1. You do the same thing, okay? You insert whatever you see here into your function. Remember, that was our strategy. We are inserting x to here so that the result is not depending on t, but depending on x. Okay, so we will do the same here too. We will insert u of x inside our function, and according to chain rule, then you have to multiply with the derivative of the u function. Okay, this is the general version of fundamental theorem of calculus part 1, which we will apply here. You can take this minus sign out from the derivative, obviously, because it's just a constant multiple there. And then you have this. Now we are ready to apply fundamental theorem of calculus part 1. So it goes like this minus is here. So what you do? This is your u of x. You will insert this function into this function here. So instead of t, I will be writing square root of x. Okay? So it goes like sine t square, right? But instead of this t variable, I will write whatever I see here. Square of this. So instead of t, I will write square root of x, what is explained here. And then I need to multiply with the derivative of the ux function. So this is our ux function. So derivative of it is 1 over 2 square root of x, okay? So this is the generalized applied version of it, okay? And then we can move on. So next example, our next example is this one. Y function is given, and we want to take the first derivative of it with respect to x. So, of course, we will start with the most outer function, you know. That's why we will first derive this power. 3 comes down, you subtract 1 from the power, you don't touch inside. T cubed plus 1 to the power 10 dt, and then you keep multiplying with the derivative of the insider functions. So I need to multiply with the derivative of this insider function. T cubed plus 1, like this. Okay, by taking this derivative now, we will, of course, apply fundamental theorem of calculus part 1, FDC part 1. Integral, then derivative. This means that please apply fundamental theorem of calculus to get the result as fast as you can. So what you should do is you will insert whatever you see here for the t variable of your function. So it is x cubed plus 1 to the power 10. So normally if this would depend on x, like u of x function, you would multiply with the derivative of the u, but it is not needed because you just have x here, right? So this is the result if we want to write it again from the beginning. T cubed plus 1 to the power 10 dt squared times this, which is the derivative of the insider function. Okay, let's move on. Now, still we want to find the derivative of the given y function by applying fundamental theorem of calculus part 1. And here, we should be careful because, okay, let me write what we want to do. 2 to the power x and e to the power x squared 1 over square root of t dx. T dt. Okay, this fits to the structure of fundamental theorem of calculus, but okay, this is our u of x, but you see there is no constant here. You can apply FTC as long as you have a constant at the upper bound. So should be a constant. That's why you need to divide the integral into 2 parts now, okay? At some point. What I mean is, okay, so let's divide the integral into 2 parts. You can choose any real number like 0 to make the things clear for us. 1 over square root t dt plus then from 0 to the to this given upper bound, of course, like this. And then you can distribute the derivative over the sums. So what is this? It is the derivative of the first expression and then derivative of the second expression, of course, e to the power x squared square root t dt. And you see now these two parts we can handle. Here, you should just first change the places of the upper lower bounds. You have to switch them, and that will give you a minus in front of it from 0 to the power x, 1 over square root t dt, and this is already in a nice form that we can apply the fundamental term of calculus part 1. Okay, now we are ready to apply it. And I need to indicate the tools that I am using now. This is what? This is the u of x part. You see, to the power x, not just x, but u of x. And this is another function. Okay, let's call it v of x. So you insert this u of x to here, okay, to your function as the variable t, 2 to the power x, and then you will multiply with the derivative of u of x, okay, which is itself times ln 2. So this comes from the derivative of the u of x part, plus we will be applying fundamental term of calculus part 1 once again. So this is another function v of x, just insert it to your t variable here. 1 over square root e to the power x squared times the derivative of this function, right? Derivative of exponential function is itself times the derivative of the power. So this comes from the derivative of v of x. And this is f u of x, and this is the function f evaluated at the v of x boundary. And that is always what you should do if you have functions depending on x for both lower and upper bound. Because to be able to apply fundamental term of calculus, you need to have constants at the lower boundary. Only then you can apply fundamental term of calculus part 1. And this example is in fact the most general version of fundamental term of calculus. Let's state it in the general form. More generally, if you want to apply fundamental term of calculus to the integrals in this form where both lower and upper bounds are depending on x, you want to take the derivative with respect to x, we understood what we should do here. So the result is f evaluated at the lower bound. Okay. So I called the upper bound as v of x and the lower bound as like this. So the result is, in the example, we see that f evaluated at the upper bound and f evaluated at the lower bound, and then you take the difference, okay? So I will write it as, you will insert it to here, upper bound, multiply with the derivative of it, and then minus f evaluated at the lower bound, and then you multiply with the derivative of the lower bound function, okay? I think I need to, so let me, this was the lower bound, and I named the lower bound as v of x here, so let's change this to parts like the notation. I called the lower bound as v of x, and the upper bound as u of x. So then, okay, this will be also, this is what we have as the v prime of x. derivative of the lower bound, we inserted it, and you have minus sign in this part for the lower bound part, okay? And here what we are doing, this is the derivative of the upper bound for the integral, and you insert u of x here, just like we write in the general formula. Okay, this is the most general form of fundamental theorem of calculus part 1, FTC part 1, where you both have functions in the upper and lower bound, and that's how you should apply it. And this is the example of it. So let's move on. Determine f5 if f is continuous and satisfies this equality. So we want to find this value. So we are given this equality. If we take the derivative of both sides, for example, then we may obtain some information about f, not about its integral, but we want to find something about f, so I want to get rid of this integral. That's why I'm taking derivative with respect to x, okay? So 0 to 4x plus sine pi x ft dt, and derivative of the right-hand side is just 2x, right? And this is something that we can apply fundamental theorem of calculus part 1. So I will insert this to variable t there. Then I get t of 4x plus sine pi x. What I'm using here is FTC part 1. But since this is not just x, but u of x, I need to multiply with the derivative of it, right? So let's do this derivative multiplication. Derivative of this thing is 4 plus cosine pi x times pi, right? Equals 2x. This is ux, and this is u prime of x. Now we can try to insert some point to obtain f5. So that crucial point is this one, 3 over 2. If you insert 3 over 2, let's see what happens. 4 times 3 over 2 sines 3 pi over 2 times 4 times cosine 3 pi over 2 times pi equals 2 times this. Okay, what is sine 3 pi over 2? This part makes 6, this is minus 1, and cosine 3 pi over 2 is obviously 0. That's why you obtain f of 5 times 4 is just 3, and this gives you the result as 3 over 4. Okay, so let's move on fundamental theorem of calculus part 2. Okay, now part 2 we are covering. And this time, as I said, we are changing the orders of integral and derivation. And I want to emphasize something here. Big letter f is given as the antiderivative of f, meaning that f of x is in fact the first derivative of the big letter f function. So what is written here is then you want to integrate f, right? In fact, you are integrating this big letter f first derivative function. Okay, so this time we are applying first derivative, then integral. In part 1, we were first applying integral, then derivative, but now we switched order. First derivative, then integral from a to b. Again, the derivation and integration will neutralize each other, and the result of this thing will be the result of the integral, okay, derivative, then integral, so you will end up with your original function, and then you have to evaluate it at this upper lower bound, so the result is like this. Okay. So let's look at the first example. We are trying to integrate this function, and then the result should be the antiderivative of what you see here, okay? So this function is the antiderivative of this f function. Okay, so tell me, what is the antiderivative of secant square? You should tell me something whose derivative is secant square. So that function is tangent t, or is just a constant multiple there. And then pi times, what is the antiderivative of t to the minus 2? You know how to take antiderivatives of power functions. Maybe I can put a recall here. We gave the antiderivation rule for power functions in the previous sections. Antiderivative is, in fact, integral. You add 1 to the power, you divide by the same power. So you have t to the, this part is pi times t to the power minus 2. That's why you will add 1 to the power and you will divide by the same power. And then, as you can see, this is a definite integral, right? So you need to insert upper lower bounds. Minus pi over 3 to minus pi over 4. Okay, then you can obtain the result as tangent minus pi over 4 plus, what is this? This is in fact minus pi over t. So instead of t, I am applying minus pi over 4. Then subtract this lower bound. 4 times tangent minus pi over 3. And then minus pi over this number. Minus pi over 3 again. Okay, so the result is then, this is obtained where t equals this value, the upper bound. This is written for t equals the lower bound. And the result goes like 4 plus minus 4 plus 4 plus 4 square root 3 and minus 3. So you will find a result like this. Okay, the crucial point in this example is the following. You have a function f here, and the integral of that function is in fact the antiderivative of it. You will think like a function whose derivative is secant square, so tangent t, right? So like that. Okay, let's move on to this example. Now, tell me something. Okay, recall. What is the derivative of arctangent function? It is in fact 1 over 1 plus x squared, right? Now, what do you see here? 1 over square root 3 dx over 1 plus 2x squared, right? And now you should tell me some function whose derivative is this thing. Okay, as you can see here, if it would be 1 over 1 plus x squared, it would be arctangent x. So instead of x, we have arctangent 2x, right? Okay, obviously, let me write it here. Arctangent 2x, if you derive it, what we obtain? 1 over 1 plus 2x squared, but don't forget to multiply with the derivative of this insider function, which is 2. And you want to get rid of this 2 here. You see there is no 2 coefficient here. That's why if you start by taking the derivative of not arctangent but 1 over arctangent 2x, you will get rid of that 2 multiple there. So 1 over 2 was already here. That's why they are gone now. That's why the antiderivative of this function is in fact 1 over 2 arctangent 2x. Now you are ready to evaluate this antiderivative at the given upper lower bounds, right? Okay, so the result is then 1 over 2 arctangent 2 over cube root this minus arctangent 0, okay? And then the overall result is 1 over this number, because, you know, this is 0. And I will just leave it like this. Okay? And finally, in this video, we can look at this example. Determine f5 if it satisfies this. Now, we will integrate the left-hand side. What is this integral? Tell me a function whose antiderivative is t squared. So you are antiderivating this. You add 1 to the power, you divide by the same power, and then you are inserting upper-lower boundaries. Right? And the right-hand side is given like this. So what you have in the left-hand side is, in fact, f of x cubed over 3 minus 0 over 3 is this number, is this expression, sorry. So your f of x is in fact 3 times this thing. So f cubed is this thing. That's why I also need to take the cube root of it. So this is your f function. Now I want to find f of 5. It is easy. I can just insert 5 for x. So the result is insert 5 for x, 60 plus 3 sine 5p cube root. Sine 5p is obviously 0, so the result is cube root of 60. Okay. So I stop here for this video. Thank you for your attention.